Hello, Noah Boss here, and this is your climate change update for January 2025. The theme of today's update is Uncharted Territory, Earth's Energy Imbalance, and I'll begin by reading the opening statement from the 2024 State of the Climate Report. We are on the brink of an irreversible climate disaster. This is a global emergency beyond any doubt. Much of the very fabric of life on Earth is imperiled. We are stepping into a critical and unpredictable new phase of the climate crisis. These are strong words for an academic paper, but when considering how many climate change indicators are heading into uncharted territory at an unprecedented rate, it becomes clear why the authors chose such strong language. This video will be primarily focused on the fundamental drivers of climate change, but in future videos I'll be covering a wide range of topics related to climate change, so if that interests you, make sure you subscribe so you don't miss any future videos. Now let's get to it. This graph shows the record of global average temperature, defined as the temperature of the atmosphere measured 2 meters above the Earth's surface. The data comes from 5 independent datasets, each produced using slightly different methods. However, as you can see, they all show very similar trends and values. 2024 has now become the warmest year on record, surpassing 2023, the previous record holder. 3 of the 5 datasets place 2024 at more than 1.5 C above the reference period of 1850 to 1900. While the other 2 are just slightly below that threshold. This makes 2024 widely regarded as the first single year to exceed 1.5 C, an important milestone, as 1.5 C was the target nations aimed to avoid surpassing under the 2015 Paris Climate Agreement. It is important to note, however, that most scientists don't consider a single year above 1.5 C as a breaching of the Paris Climate Agreement target. The Paris Agreement intended the 1.5 C threshold to reflect a longer-term average, though there is no universally agreed upon method for determining when this average is reached. Some propose using a 10-year average, while others suggest a 20 or even 30-year average as the standard. Even so, there is a rapidly growing consensus that the 1.5 degree target is no longer feasible. The Berkeley Earth Global Temperature Report for 2024 states that recent warming trends and the lack of adequate mitigation measures make it clear that the 1.5 C goal will not be met. And in the Copernicus Global Climate Highlights for 2024, it is stated that the probability of reaching the 1.5 C target of the Paris Agreement within the 2030s is highly likely. In a recent 2023 paper authored by James Hansen and colleagues, it is stated that they expect the 1.5 C threshold to be breached in the 2020s and 2 C before 2050 under the present geopolitical situation. James Hansen has even gone on record saying he personally considers the 1.5 C threshold already met, considering the current high rate of warming and the fact we are already seeing temperatures well above 1.5 C during the most recent El Niño. In fact, over the last 2 years, we have seen individual months above 1.7 C and even a handful of days above 2 C for the first time. In addition to atmospheric temperatures, we have also been breaking records for sea surface temperatures and ocean heat content for the past 2 years. The graph on the left shows the global ocean heat content anomaly, which measures the departure from a baseline, in this case 1981 to 2010, of the total heat content in the ocean from the surface down to 2,000 meters, measured in zettajoules. 1 zettajoule is equal to 10 to the 21st joules, or 1 sextillion joules. To put that amount of energy in context, 1 zettajoule is equivalent to nearly 16 million Hiroshima bombs, and with an increase of around 300 zettajoules since the 1981 to 2010 reference period, that would be equivalent to nearly 5 billion Hiroshima bomb explosions worth of energy. This data, presented by Chang et al. In a recent paper titled Record High Temperatures in the Ocean in 2024, is accompanied by this statement from the authors. The increase in the ocean heat content rate in recent decades indicates a multi-decadal acceleration of ocean warming. Ocean heat content is an excellent way to estimate the rate of global warming for 2 reasons. One being that 90% of the heat from global warming is absorbed by the oceans, and the other being that this data has far less noise than atmospheric data, which is due to the high heat capacity of water, resulting in less year-to-year fluctuations. The graph on the right shows sea surface temperatures, which only captures the heat at the very surface of the oceans, and therefore more closely resembles the data for global surface air temperatures, as it is strongly influenced by short-term fluctuations such as the El Niño Southern Oscillation. Further confirmation that global warming is accelerating can be found in the satellite measurements taken by NASA through the CERES program, which stands for the Clouds in the Earth's Radiant Energy System. This program monitors Earth's energy budget by measuring the amount of energy entering and leaving the planet's atmosphere. By analyzing solar radiation reflected by clouds, aerosols, and the Earth's surface, as well as outgoing long-wave radiation, CERES provides critical insights into changes in radiative forcing. If more energy is entering the Earth's system than leaving, the planet has a positive energy imbalance and will warm. If these two values are equal, the planet's temperature will remain stable, and if there is more energy leaving the planet, it will cool. The satellite record, which goes back to the year 2000, when the satellite instruments first became operational, shows a constantly increasing positive energy imbalance. This evidence points towards an acceleration in the rate at which our planet is absorbing heat, with an approximate doubling since the early 2000s. This graph represents the same data as the previous, but breaks down the energy imbalance into its two principal components: absorbed solar radiation and outgoing long-wave radiation. Absorbed solar radiation, which is represented here as the orange line, is the difference between the total amount of sunlight striking Earth and the amount of light that is being reflected back to space. Any energy that is received from the sun and not reflected is being absorbed into the Earth's system. The blue line is depicting the outgoing long-wave radiation, and the difference between these two values is the Earth's energy imbalance, which can be seen as the shaded yellow area on the graph. The effect of increasing greenhouse gas concentrations is to reduce the amount of outgoing long-wave radiation for a given surface temperature. This results in a positive energy imbalance, which only subsides after the surface temperature increases to the point where the outgoing long-wave radiation again equals the amount of absorbed solar radiation. However, all else being equal, this equilibrium will not occur unless the greenhouse gas concentrations stop increasing and remain stable. Another way for the energy imbalance to become positive is for the amount of absorbed solar radiation to increase. There are two possible ways for this to happen, the first of which being natural cycles, such as changes in the sun's energy output or through fluctuations in the Earth's orbit and tilt. The other being changes in the reflectivity of Earth. Since natural changes to absorbed solar radiation are well accounted for, and either too slow or too small in magnitude to account for this increase in absorbed solar radiation, it can be determined that a change in Earth's reflectivity is the primary driver of the current increase. This means that the Earth is becoming less reflective and is absorbing a greater portion of the sunlight striking it. Reduced snow and ice cover, changes in cloud cover, and changes in the reflective particles emitted during industrial activity are contributing to this decreased reflectivity. You may have noticed that, despite the greenhouse effect I mentioned earlier, outgoing long-wave radiation has actually been increasing steadily for the last decade. While this is counterintuitive at first, a better understanding of what determines the amount of outgoing radiation leaving Earth will clear any confusion and also provide an important insight into the major reason for the acceleration of global warming in recent decades. The amount of outgoing radiation of an object can be determined through the Stefan-Boltzmann equation. The important takeaway here is that, for a given increase in temperature, the amount of energy that is emitted by an object increases by a proportion of its temperature in Kelvin to the fourth power. This creates a powerful stabilizing effect for Earth's climate known as the Planck feedback. As the planet warms, it emits more radiation, resisting further temperature increase. Increasing greenhouse gas concentrations reduce the outgoing radiation by trapping heat, though greater amounts of these gases are needed to sustain additional warming. Understanding this fact is important for understanding how outgoing radiation can be increasing despite an increase in the greenhouse effect. Because a large portion of the increase in the temperature is now being driven by the Earth becoming less reflective, the total amount of outgoing radiation is increasing despite the increasing greenhouse effect. This visualization helps depict how the greenhouse effect is still substantially contributing to the energy imbalance of the planet despite increasing outgoing radiation. If the greenhouse effect was less substantial, the amount of outgoing radiation would be even higher than it is, leading to a smaller total energy imbalance of the planet given the same change in absorbed solar radiation. Now that I've established that the rate of warming is accelerating, it's time to explore why this is happening. What are the key factors driving such rapid changes in our climate? The first topic I'm going to cover are the three most significant greenhouse gases that society emits: carbon dioxide, methane, and nitrous oxide. Carbon dioxide is by far the biggest contributor to climate change at 80% of the total anthropogenic effect, with methane coming in at a second at about 11% and nitrous oxide at about 6%. A group of compounds known as fluorinated gases make up the remaining 3%, but since their combined effect is relatively small, I will not give a detailed summation of these gases in this video. First off, let's look at the record of atmospheric carbon dioxide levels taken from the Mauna Loa Observatory. As you can see, carbon dioxide concentrations continue to increase in the atmosphere year on year, with the most recent monthly average taken in December of 2024 being 425.4 parts per million, which is a growth of 3.5 parts per million over the previous year. This represents an increase of 52% over the pre-industrial value of 280 parts per million. It is also apparent that the growth rate is continuously increasing, resulting in a steeper increase as time goes on. Adding a straight line to the data shows this clearly. In order to get a more objective look at how the rate of CO2 growth is increasing, we could look at the year-on-year growth values. A very clear trend of greater annual increases in CO2 concentrations can be seen, with 2023 breaking the record for the largest annual increase in CO2 concentrations since the beginning of the dataset. 2023's annual increase was substantially greater than the average for the 2010s, which saw the greatest increase of any decade and came in at 2.43 parts per million per year. This graph shows global CO2 emissions from industrial activity, which reached a record high in 2024. Considering the record rates of growth in atmospheric concentrations combined with record human emissions, we should not expect carbon dioxide levels to stop increasing anytime soon. Now I will move on to atmospheric methane. Methane is a much more complicated story and deserves a video of its own, which I'm sure to release at some point in the near future. But for now, I will just give a quick overview of the current trends. The most recent monthly average available for methane is for September 2024, which came in at 1,936.64 parts per billion. This is 11.58 parts per billion growth over the same month a year prior. Pre-industrial methane levels were close to 700 parts per billion, meaning current levels are a 176% increase over the pre-industrial levels. The record for atmospheric methane looks quite different than CO2, with a strong growth rate before the 2000s, a brief pause in growth in the early 2000s, and a resumption of high growth rates ever since. This graph, which plots the growth rate of methane, shows this behavior more clearly. In the 80s and 90s, the growth rate gradually decreased, then remained near zero from about 2000 to 2006, then began growing again until the present day, even reaching an all-time high in 2021. The current 10-year average is 10.93 parts per billion per year, which is similar to the rate of growth before its pause. There is still some debate and uncertainty as to why methane emissions paused in the early 2000s, then resumed growing until present day, which is a topic I will cover in a future video. And the last greenhouse gas I will cover is nitrous oxide. The pattern of growth is a lot more similar to carbon dioxide with a clear and gradually accelerating trend. The most recent average for September 2024 was 337.72 parts per billion, an increase of nearly 1 part per billion over the previous year, and an increase of 20% over the pre-industrial level of 280 parts per billion. Similar to the previous two gases, this graph is showing the annual increase in nitrous oxide, which shows that the rate of growth is increasing over time. Scientists have been warning humanity for quite some time now that the growth of greenhouse gas concentrations must be halted in order to prevent the worst impacts of climate change. And as I have just shown, not only has this not happened, but in the last decade, the growth rate for all three major greenhouse gases have reached unprecedented highs. So where does this put us in respect to the climate model scenarios that scientists use to project future temperatures? This graph clearly shows that, while we are slightly below it, RCP 8.5 is the closest scenario to the current annual growth of greenhouse gas forcing. Many of you probably already know that RCP 8.5 is known as the worst case scenario and includes no mitigation measures to prevent catastrophic climate change. The gap between current greenhouse gas forcings and the lower scenarios designed to keep us between 1.5 and 2C is stark. In order to put current carbon dioxide levels into a better context within Earth's climate history, we could use proxy data such as ice cores and other paleoclimate methods to estimate CO2 levels of the distant past. The graph on the right is a reconstruction of atmospheric carbon dioxide levels using the analysis of small bubbles of air trapped in ice cores that go back as far as 800,000 years. Because we could directly measure preserved samples of the atmosphere, this is considered a very reliable method to get an accurate picture of the atmospheric chemistry of the past. As you can see, carbon dioxide levels are well above anything experienced in the last 800,000 years. Using a combination of other paleoclimate proxies, we can recreate a history of carbon dioxide levels going much farther back than 800,000 years, though this comes with the caveat of larger uncertainties due to the lack of direct measurements. Still, researchers have concluded that it's likely that you would have to go back around 14 to 14.5 million years before you see carbon dioxide levels as high as they are today. The fact that humanity has done this in the span of about 100 years, with over half of that increase happening in just the last 40, puts into perspective just how unnatural this increase is. Now that we have covered the greenhouse effect in more detail, it's time to focus on changes to the Earth's reflectivity, commonly referred to as albedo by scientists. As I mentioned earlier, the albedo of Earth is a very important property of the climate system, as it determines how much of the incoming solar radiation is absorbed by the Earth's system, as opposed to being reflected back into space. As this image indicates, snow and ice are very important to Earth's albedo, as they reflect a high percentage of the incoming light. This graph plots the satellite-derived measurements for sea ice extent, which began in 1979. The dark blue line shows Arctic sea ice extent, the light blue line Antarctic sea ice extent, and the red line shows both of these values added together to show total global sea ice extent, with its own axis on the right. While the Arctic sea ice has been declining throughout the satellite record, Antarctica has actually seen a growth of sea ice lasting until 2014, but the last 10 years has seen a steep decline to new record lows. When looking at global sea ice extent, an accelerating decrease is observed throughout the satellite record. With a decline of 2.2 million square kilometers when comparing the 2010s average to the 1980s average, this represents a large surface area of the planet that is no longer reflecting radiation during summer months, but instead being absorbed into the dark ocean. It is hard to visualize what 2.2 million square kilometers looks like, so as a comparison, that equals roughly 24% of the land area of all 50 US states, or nearly 13 times the area of Florida. This graphic uses the same satellite data presented earlier to determine the Earth's energy imbalance, but it is broken down by region. A very obvious growth in the energy imbalance can be seen in the region where significant Antarctic sea ice loss has occurred over the last 10 years. The change in energy imbalance is more modest over the Arctic region in this graphic, but it is important to note that these values are a comparison of the 2010 to 2019 average to the 2020 to 2023 average, and much of the loss in Arctic sea ice occurred before 2010, while Antarctica saw its steepest declines during the period shown here. You could also see that large regional increases to the energy imbalance occurred over the northern hemisphere oceans, particularly the North Atlantic, which brings us to the next phenomenon that has contributed to the decrease in Earth's albedo. In addition to greenhouse gas emissions, the burning of fossil fuels and biomass also produce small reflective particles referred to as aerosols. These particles act to reflect sunlight, increasing albedo and partly offsetting the warming influence of greenhouse gases. Unlike carbon dioxide, these particles are very short-lived in the atmosphere and are removed in the time span of days or weeks, whereas carbon dioxide remains in the atmosphere for hundreds or thousands of years. Sulfur dioxide is a particularly important aerosol due to its properties making it effective at reflecting sunlight. Not only does sulfur dioxide reflect sunlight directly, but its effect is magnified due to its ability to assist in the condensation of water vapor. The abundance of sulfur dioxide in the atmosphere can both increase cloud cover and make clouds more reflective by decreasing the average cloud droplet size. It is important to note that while aerosols slow global warming, they are very harmful to human health and the health of the environment. In recent decades, environmental regulations and a shift towards cleaner burning fossil fuels such as natural gas have led to a reduction in global sulfur dioxide emissions, while greenhouse gas emissions remain at record levels, which is resulting in a boost in the rate of global warming. Recently, a regulation resulting in an 80% reduction in sulfur emissions in international cargo ships, which took place in 2020, has been of particular interest for scientists trying to determine why global warming has accelerated faster than expected in recent years. The small red line on this graph shows international shipping emissions of sulfur dioxide, and a sharp drop-off in 2020 is apparent. While this is a small portion of the global decline in aerosols, there are reasons to believe that this decrease has a proportionally larger impact on the energy imbalance because it is occurring over the oceans, where the atmosphere is relatively devoid of other sources of aerosols, and the dark ocean absorbs a large amount of radiation that is not otherwise reflected. This graphic gives a good picture of the spatial distribution of global sulfate emissions from shipping, as well as showing that a large percentage of the total sulfates in these areas come from shipping. You can see that a majority of shipping occurs in the northern hemisphere oceans, which is in line with where the greatest increases in the energy imbalance has occurred since the 2020 regulation was enforced. While scientists are still trying to determine how large of an effect this regulation has had on the energy imbalance of the planet, early indications are that this effect is likely substantial. This paper found that estimated radiative forcing averaged over the global ocean was 0.2 watts per square meter, which is enough to more than double the rate of warming in the 2020s as compared to the rate since 1980. The change in forcing from this regulation should theoretically lead to a temporary acceleration in warming, though the jump in temperature is permanent, leading further credibility to the idea that we may already be breaching the 1.5 degree target. And that's all I have for you today. If you enjoyed this video, please don't forget to like, share, and subscribe. It really helps support the channel. I'd also love to hear your thoughts, so feel free to leave a comment below. In my next video, I'll dive deeper into the changes we're seeing in the oceans and cryosphere as a result of climate change. So stay tuned for an in-depth look at these vital components of our planet's climate. Thanks for watching, and until next time, take care.